Alrighty. So I unfortunately have no interesting stories about John Dowling. I never met John, and coming to this conference and hearing everything what you have to say, I realize that's a shame. It sounds like I find it interesting that most of the things that I've heard about him are about him as a person, not him as a physicist. I haven't heard about all of his achievements, all the great discoveries he's made. And I'm not saying that means he didn't have them. I'm just saying that tells me that he was a great person and a great friend to a lot of you, which I think is a good way to remember him. Anyway, this talk is about some research that I've done over the past, over my PhD. I'm towards the end now. And if you were at AIP a month or so ago, you may have seen the shorter version of this talk. I've added a couple of things to pad it out, I guess, but just to give you more details. And hopefully this time you'll have some more time to ask questions. So please do. I'm happy for you to stop me. So this is a cluster state. You've seen them over the past two talks. Ben and Nick showed you examples of them. Essentially, we have all of these nodes here are zero momentum eigenstates. They could be GKP states, though, as Ben talked about. But for the moment, I'm just talking about them being zero momentum eigenstates connected by some entanglement operation between them. And it creates this cluster state. And this is what we call the quantum computer. You measure it, and it does stuff as an input state is teleported along. Choosing your measurement basis allows you to choose the operation that gets done. But I want to talk specifically about teleportation just to highlight that fact. And hopefully this doesn't get too redundant based on the previous talks, but I'll try not to waffle on too long about it. Again, this goes from right to left. So we have an input state over here, and then an ancilla state, which I'm just calling psi, and a measurement, which is a bra on the left. And this is a momentum basis measurement, and M is the outcome of that measurement. And this teleports the input, this measurement teleports the input state into the output. There it is, like there, input. But it has some operation applied to it, K for Krauss operator. This is the Krauss operator that Nick was talking about. And this Krauss operator depends on two things. It depends on the measurement outcome. And so that may mean you need to do some type of correction to shift your state back. But it also depends on the input state, psi. But I'm adding another degree of freedom. I'm saying that instead of just momentum measurements, we have this p theta measurement, which is just a rotation in front of the momentum measurement. And that angle of the rotation, theta, is another degree of freedom we have. So we're just changing the angle with which we're measuring our state. And that changes the Krauss operator. So in the picture previously, all the all the ancilla states were zero momentum states. So that picture kind of removes that degree of freedom. M is something we don't get to choose. That's just the outcome. That's just something that happens to us. So we don't get to choose that. But theta, we do get to choose. So with this, we have freedom to choose what K is. And we know everything else about K as well. So that's kind of the basic idea of teleportation in this cluster state. And so I've just highlighted two groups of nodes here. The first being this one here, which in the canonical case is sufficient to do a single mode gate. And this set of modes here, I'm losing the, not sure. Oh, here we go, we found it. This is sufficient to do two-mode gate. So you have these connections between, as Ben mentioned. But in order to actually do a quantum computation, we need some idea of a qubit. We need some idea of a logical state, which again, here's the GKP state. And just to kind of emphasize again, this is the position wave function of the, make sure I get it right, in the black, the zero logical state, and the position wave function of the one logical state in the red. And so, yeah, there's just that shift that takes you from 0 to 1 and back again. I will mention another state, which is neither 0 nor 1, but it is what we term Q0 state. And this state does not carry logical information, but it does carry the encoding. It has a different spacing. It has a spacing of the square root of 2 pi, but that spacing is the same in position and momentum. So you can do a Fourier transform on this state and it doesn't change. That allows you to use, if you're generating GKP states, for example, this is the state you'd want to generate because you can use this state. Well, I'll show you how you use it in a little bit, but essentially, you don't have to worry about changing pluses to zeros or anything like that. This is the one state you generate. So it doesn't carry information, but it carries the encoding. And you can use it for error correction. But how do you use these GKP states? So Ben already mentioned this, so I guess this is redundant now, but you kind of can plug them in on the top of your cluster state and then measure them and teleport them into your cluster state. That's one picture of how you might get them into your cluster state. But all this is canonical. Nothing, don't even ask me what physical things are going on here because there's nothing physical going on. This is just a nice picture at the moment. And so, but I'm going to go over noise accumulation again, but I'll try to do it quickly. So you start with a nice state. It's got these peaks. You do something to it and the peaks get wider, noise gets added. Noise gets added again when you do something else to it. So each step along here, I'm measuring and I'm doing some particular measurement, applying an operation, but along with that operation comes noise. And that noise is just inherent to the fact that it's a continuous variable system. Anyway, so noise gets picked up, but then we teleport onto the GKP state now, and our noise gets fixed. Let me go back. I didn't realize it was going to end. So I'm just doing the one side now. This will correct like the noise in position, and then along the next step you do a Fourier transform, and then also correct in momentum as well. So you get the two quadratures in that way. Okay. All right, so here we are. This is the paper where all of what I just said is all encapsulated in here, in this 2014 paper. But since then, of course, we have actual cluster states that actually get made with actual physical equipment. And this is one example of a single mode cluster state. So this is equivalent to, I'll tell you now, it's equivalent to this sort of thing. Ignore GKP. It's equivalent to this little line of nodes. So you have two optical parametric oscillators that give you some squeezed light, and you logically slice it up into time bins. And then you interact them via a beam splitter to create these two-mode squeeze states. After delaying one of them, you then interact them with another beam splitter. And so the second beam splitter, if you didn't do the delay, would of course undo the two-mode squeeze state. But because you delayed, you're interacting them with the nearest neighbor or some other neighbor, depending on your time delay. And instead, it creates this more complex entanglement structure where the blue and the yellow are a different weighted entanglement that depends upon the squeezing at the start and all that. But the point is that you have some complex entanglement structure like that. This other paper did the same thing, except did it for a real long time. So the point is that they can make these states very big. And these other groups using, the same group and Anderson's group here made two-dimensional versions of this state with similar techniques, obviously different, but they end up with a similar state at the end. So one of the big things I'm going to be talking about in this paper is how these different states compare. So just to kind of give you an idea of what to expect. In any case, the point of this slide is just to say that they can make really big cluster states that kind of look like what we're talking about before. Look, it's kind of a square grid. But if you look too closely, it stops looking like it anymore. So just stand back. So here we are. Here's a direct comparison. They're kind of the same, but they're not at all the same, which is the best type of physics. But if you, in this paper here, Ralph Alexander was the first author there, showed that you could look at that more complicated cluster state and kind of just group the pairs vertically and then ignore the rest of the entanglement and say that now we have a bunch of macro nodes with two local modes inside them, and they're all connected by this entanglement here, which is much more similar to the canonical case. So that's good. But on top of that, they showed that you can do a distributed measurement across these two modes, which teleported an input state across the next macro node and applied an operation based upon the measurement basis. So this is consistent with everything I just told you before, but instead of just looking at local modes individually, you're looking at macro nodes now. And so we call these cluster states now, we call them macro node based cluster states, because once you look at them from a macro node perspective, they look the way we want them to. So this is, I've got up there in yellow, quad rail lattice. So that is what this two-mode cluster state is called. And it, again, we have a couple of things going on here. So let me just highlight something. So at the top there is basically what I just showed you a second ago. So it's that wire, which I'll call the macro node wire. And it's just coupled into its macro nodes. The arrows are beam splitters. I mean, I've got it written there, so those of you who are quick would have seen that already. But this is the macro node wire. And this is what, sorry, went the wrong way. And this is what this simplified view is showing you. But essentially, this paper showed that, showed how to measure the macro node wire in order to teleport the information and in order to do operations. So we know how to do that. But let's look at the two-mode states. How do you do it for these two-mode states that are really complicated? So this is the two-mode macro node. You can think of it, there's two ways of thinking about this, right? The standard way is you've created a two-mode state and you collect it up into two-mode macro nodes. And this is going to get annoying because probably I didn't think too much about the terminology beforehand. But these two-mode macro nodes have 4 local modes in them. But it's a macro node on a two-mode cluster state. That's the point. So yeah, I was talking about 2 different ways to think about it. So one way of thinking about it is that you've got this large two-mode cluster state that's got all these complicated lines showing entanglement going everywhere. You group them into groups of 4 modes, and you say that's a macro node, and that's how I'm going to see the cluster state. The other way is to just group them into these standard macro nodes, into macro node wires like this, the rows. And then you have a two-mode cluster state that is macro node wires connected with beam splitters between them. Now, the reason why we want to do this is because now we can take the same results from the macro node wire and just plug them directly into this one. And so essentially we can write down a circuit. I mean, it's right there, but you write down a circuit for a single two-mode macro node measurement. So that's 4 local modes being measured at the same time or close to the same time. And so the circuit is just this. Again, it's right to left. And it's simply 2 input modes, in and in, connected by a red beam splitter. This red beam splitter. So all that kind of goes across. And 4 ancillas here and here that have been connected by beam splitters already. I won't go through all the details, but essentially it's kind of a one-to-one mapping of all the beam splitter styles and things like that. But the important part is that I won't actually go through it because it's reasonably simple once you know it, and it's just annoying to go through in detail on a slide. But you can write it down as this Krauss operator. It just has 2 inputs and 2 outputs. And this is the 2-mode operation that happens. That depends on theta A, B, C, and D, which is the angle of the 4 measurements. It depends on the measurements, MA, MB, MC, and MD. And it depends on psi, phi, that are the ancilla states. So this is the equivalent of that simple teleportation that I showed you at the start. And the important thing is that we can choose theta. So we can choose what this V is. And this V, I think my next slide will actually show what it is, I believe. But we can choose what this V is. And so we know then what the displacement is. So we know any corrections that need to be done. And this A, well, I mean, the important part about this A is if you have GKP in those ancillas, the A is just the GKP projector, it just does error correction. If you only have one GKP state and the other one has been swapped in with a zero momentum state because your GKP state generation failed, then it's just half error correction, like what Ben mentioned. So if you only have one GKP state, you just do half error correction. And so that A just depends on what the ancillas were. But the important part is this general two-mode gate. So we have a general formula for what our two-mode gate is going to be based on the angles that we choose. And so as well as the single mode gates, which was previously already thought out in the noise analysis paper, for the two-mode case, we've shown that you can do the GKP Clifford gates, like the CZ gate, based on this choice of angles, not that the specific angles matter too much at this point. And so essentially this is just showing us that your choice of angles can enable you to do all the CV unitaries that correspond to the GKP Cliffords. But the most important thing is that this is in one step. So, okay, that's what Kai is, don't worry about that. So in a single step, you can do all of these. Now, if I go back a little bit, apologies, you'll notice if you're looking at these, you're teleporting through a number of different modes. You've got to do these two modes as well. The point is that the more teleportations you do, the more modes you push yourself through, the more noise you collect in order to do a single gate. This is a single gate. And previously, it was thought that in order to do this gate, in order to do a single mode gate, you need to do 2 steps of teleportation. So we've shown you actually only need this part to do a single mode gate. And the same thing for a 2-mode gate, although I don't have a picture to show that as clearly. So we're using up half the modes to do the same gate. That enables us to reduce the squeezing required in the cluster state in order to achieve an error rate, a given error rate. So you want to do logical error correction on top of after you do the measurements and things like that, you do GKP error correction, do all that, you need to do some logical error correction afterwards. Because as Nick and Ben mentioned, the GKP error correction takes the CV noise and converts it to a potential logical error. So you need to do logical error correction to fix those errors. And so if your chosen error correction scheme requires a certain error rate, you need to have your cluster state squeezed to a certain level in order to enable that. And so this work reduced that level required. So we don't need our cluster states to be as high quality as previously thought. Thank you. Yeah. Yes. Yeah, for a fixed amount of squeezing, that's right. And the amount of squeezing is here. So this is the paper I'm talking about. If your logical error correction scheme requires an error rate of 10 to the minus 2, then for a single gate, you need to have your GKP states and cluster states squeezed to 11.9. That's right. Yeah. Okay. But remember, this is only for the quad rail lattice. That's for one type of cluster state. Oh, and I guess we just jump through this again, right? This is exactly what I showed you before. You have an input state, you do your gate, does some noise, and then you do GQB error correction. So I'm just emphasizing it's less steps, therefore less noise, therefore you get to do error correction. Oh, sorry, less likely to incur logical error. But yeah, so what I've just talked about was for the quad rail lattice specifically. But there is these other types of two-mode cluster states that all have different structures that are all created using the same, ideas, but created slightly differently. And so there's like a range of different squeezing requirements that you would need depending on which cluster state you use. And then some discussion about which cluster state is better for what reason. However, this is from a paper from Anderson's group. First author is Mikkel Larsen, where they compare the different types of cluster state. And they have this column where they talk about, in the QRL particularly, they say no projection into Y is needed. So essentially what they're saying is, let's use this apparatus to create this cluster state, and then we can do quantum error correction. We can do quantum computation with it. But these other ones, they are first measuring in position a bunch of the modes to delete them because they want to attain this structure of wires. And the noise that was in those modes doesn't just disappear. It gets pushed around, and you end up with a lower quality state at the end. And so that's the only reason why people would say the quad rail lattice is better. What we showed is that, in fact, what we did has nothing to do with the quad rail lattice itself. This has 4 beam splitters in, so our imagination jumped to the term 4 splitter, and it doesn't actually matter what 4 beam splitters they are. There's just a 4 splitter, and we've defined it as, I won't go into exactly, but there's some constraints to how it's constructed. But if you choose another 4 splitter, you just get a different 2-mode gate in this circuit. And the same thing applies. You still have, if you can do if this V2 can do like a CZ gate in one step, then you have the same noise properties for the CZ gate in regardless of which cluster state you used originally. So the only piece that depends on the beam splitter network is this V. And so if you can do a single, I just said that, sorry. So what this work has done is taken these cluster states, which are thought of in that 2-mode macronode way. This is a macronode, this is a macronode. And I've changed it to the other way, where I've got these macronode wires connected by beam splitters. And so this is the same thing as before, but the beam splitters are just in a different order. Now, I'll quickly say, thank you. I'll quickly say these yellow ones, these green ones employ a tech, because this is the actual beam, this is the actual cluster state. There's no beam splitter here. So these green ones, we employ a technique to insert a virtual beam splitter, which I'll just show you this. We have no beam splitter here. If we alter the measurement outcome in post-processing, we can pretend that there was a beam splitter there originally. And I've got some other reasoning here, but I won't go through it all. But essentially, that allows us to say, okay, this is for the QRL. For this other one, we have a different setup of beam splitters, but it's still a 4 splitter. And the unitary matrix looks very similar. So we can use some operations that take us between them. So swap gates after the 4 splitter, swap rows in this unitary matrix. F squareds on wires after the 4 splitter, multiply rows by -1 in the unitary matrix. And F squareds before the 4 splitter, or to the right over here, they multiply columns by -1. So using these operations, which are simple to do in this framework, and can be mostly done with post-processing, we can convert one force splitter to another force splitter. And this is a simple conversion here. So this is for the QRL, the quad rail lattice, and this is for the other one, which is called the bilayer square lattice. We can do a swap and an F squared here, and it makes it the same as the QRL, which gives us the 2-mode gate for this other cluster state as well. And so all these types of cluster states, we can write down which measurement angles are required to do all of the Clifford gates and show that they have the same noise properties as the QRL. And so this discussion on which one's better, which one has better noise properties is kind of moot because they are all essentially the same with some minor constraints. And that is the end. Thank you everyone for listening.